So eddy current testing, the theory of operation is that we are going to use induction in order to produce magnetic fields and eddy currents in a material. And then we are going to also use induction to sense those eddy currents that are formed and the magnetic fields that they give off in that material. So this is an example of a single coil system. So we can have, we'll get into probes a little bit later, and we can have probes that have single coils or multiple coils in them, but the simplest type of probe uses a single coil that both produces and senses the eddy currents in a conductive material. So in order to produce a current, though, we have to have a changing magnetic field. Okay? We can create a magnet with a constant electric current. That's a DC electromagnet. But in order to induce a current in a coil, we have to have a changing magnetic field. And so the way we use that is through an AC input. So we run alternating current through our coil. That means we have a magnetic field shown here in blue that is, it builds that field, right, in one direction. And then when our current swaps or reverses, that field collapses and then builds in the opposite direction. North pole becomes south pole becomes north pole. And then that alternating current again flips direction, that coil collapses, re-expands in the other direction. Again, now south becomes north, north becomes south. And so that's where we get a constantly changing magnetic field. And every time that magnetic field changes, which here in the US, the easiest way to do it is to do it 60 times a second. Okay, that's one way to do it. Another way, our tester has the ability to put all kinds of different frequencies in. And most of the time, we're going to do it at much higher frequencies, kilohertz or even megahertz range. Okay? It can't even be done, though, at that 60 hertz range. And your oldest meters just did that. They weren't very sensitive, though. We can increase the sensitivity by increasing that frequency. So that's where most of ours are going to be in the kilo or megahertz range. So it could be, kilohertz range, it's swapping thousands of times, tens of thousands of times, or hundreds of thousands of times a second. Megahertz range, it's swapping millions of times a second. Okay, so it's effectively, there is no time where it's not changing. But that magnetic field, each time it builds and collapses, when it contacts a conductive material, again, doesn't have to be ferromagnetic, and most of the time it's not. Most of the time we're dealing with titanium or aluminum in aerospace, is going to cause small currents to form, very, very tiny currents to form in the material itself for that fraction of a second. Okay? And those are called eddy currents. That's where the technique gets its name. What those eddy currents are going to do then is each of those eddy currents is actually going to create its own little magnetic field. Now, just because we're doing this on a non-ferromagnetic material does not mean it cannot produce a magnetic field. Okay? Because while that current is running, and it is going to cause the poles of those atoms to align for that brief fraction of a second, and that will create a magnetic field for that brief fraction of a second. Now, the aluminum, titanium, now it can do this in steel, it can do it in ferromagnetic materials, but in our non-ferromagnetic materials, the aluminum, the titanium, that kind of thing, they're not going to stick around very long. They have low retentivity, or they have effectively zero retentivity. So they're not going to retain that magnetic field after that field from the coil collapses, our field coil collapses. But for that brief fraction of a second, we will get, for those eddy currents that are formed, we will get a small magnetic field that forms. And those small magnetic fields will then affect our coil. They're going to push back, offset 90-degree phase. They're going to offset the phase of the current running through that coil. And so our tester that's hooked up to this coil will be able to sense that very, very slight change in the current being run through the coil. Because once these form, these magnetic fields are going to affect the coil, and they are going to affect the current flowing through the coil. Okay, so just like we can run a current through a coil and we get a magnetic field, when we have a changing magnetic field, and again, these are changing every time the magnetic field's changing, it's causing the eddy currents to change, collapse, form the opposite direction, collapse, form back in the original direction. And that means that the magnetic fields they're producing are going to form one direction, and then they're going to collapse, and then they're going to form the opposite direction. So, all of these are changing, again, thousands, tens of thousands, hundreds of thousands, or millions of times a second with our highly sensitive equipment that we have. And so that will produce kind of an offset electromotive force in the coil. Who remembers what that's called? Okay. Kind of hand it. Okay. What is that called? What are we sensing? These eddy currents that are forming these magnetic fields. When those magnetic fields interact with the coil and change, they kind of do an offset EMF. Remember the sine waves they drew over here? What was that called? I saw Zach's hand up. They're out of phase. Well, it's going to change the resistance of the coil, but it's got a specific name when we're dealing with AC here. What's that? Inductive reactance. Okay? It's the inductance causes inductive reactance. Okay? And so our coil is picking that up, and which is effectively, Wujung, a form of resistance. Now, it's not resistance there's a certain amount of resistance just because this coil of wire, right, the electricity trying to run through it, is going to have some resistance moving through the wire. When you add the inductive reactance, you get the total impedance of the coil, which is the tool. Okay? So here's that. So here's that resistance in the coil plus our inductive reactance. And as those change, and specifically in our case, primarily as the inductive reactance changes, it's going to move the impedance of the coil. It's going to change that impedance of the coil. And it's called impedance shift. So what we have is, you can see there's 2 points here labeled Z1 and Z2. The ultimate impedance of the coil is going to be affected by the coil itself being in proximity to that conductive material, to something that can form those eddy currents and those resultant magnetic fields of the eddy currents. So any change in the material in front of the coil, even as small as a tiny crack that's too small to see, causes some kind of a shift in the impedance of the coil. And so by seeing that change in impedance, we know that something has changed in front of the coil. That's what it tells us. It tells us something has changed in front of the coil. It doesn't tell us what that something is. I said it could be, a crack that's not visible. It could be corrosion on the backside. Okay, those would both be relevant indications. But what else would cause the impedance to shift? What's that? Well, what about sparsity? What about the structure? What other things could we have that maybe would give us a non-relevant indication? What if I go from a thick area to a thin area? Say I'm going across the spar rib, I'm going across the top of it. I go from, it's T or I shaped, right? Something looks like that. If I'm bringing my probe across here, what's going to happen when I get to kind of this point right here? What changes? We're going to have more metal in front of the coil when I'm over this area than when I'm on one of these sides. So it's going to change that impedance. So I would expect to get a non-relevant indication if I was going across this top surface, for instance. Okay? One other check you're going to do is we have a block of material that's kind of shaped like this. And we're trying to find a crack. If we were to cut it, it would look like that. So a crack running down that radius. If we're taking our probe and going like this, do you think you would get the same impedance here on the little tab that you would up here? Probably not, because here you've only got this much metal in front of the probe. Over here, you've got that much metal in front of the probe. And you got much more. So you'll get different impedances, but as you go over this little crack right here, or say we had a crack right here, your probe will pick that up and you'll see an impedance shift on your display. Okay? And this display records that, essentially that position over time. And you'll see that as you use it. When you use it, you'll see it. It almost draws like I said, like you're using an Etch-a-Sketch. Okay? You'll see that point move as you go across something. Okay? So some vocab we need to know about it. So a few of these things you kind of want to understand. So current density is the amount of eddy currents that are in a given area. So before we get to what current density is, what do you think affects current density? We've got a few here. What kind of things might affect current density? I guess you could get a couple like 3 points by looking further in the slide. What do you think might affect current density? What's that? Well, that's what it is. What would affect the amount of eddy currents in a given area? What would change current density? What kind of things might change it? The what? The thickness of the material, what we were just talking about, right? That impedance is affected, the eddy currents produce a magnetic field. That magnetic field interacts with the coil. So any change in the impedance is because of those eddy currents changing. There's going to be probably more eddy currents in the thicker material, going all the way back to here than there are in this little thin tab. What other things could change in the density of eddy current? How about okay. How about the material itself? Do you think you get the same eddy current formation in a piece of aluminum that you do in a piece of steel, that you do in a piece of titanium, that you do in a piece of brass or bronze? No. Early on in the lecture, I said you could use this for material sorting. That's why you could use it for material sorting. You're going to get different densities of eddy currents in different materials. Ferromagnetic materials produce really strong magnetic fields. Those magnetic fields are going to produce a lot of eddy currents, right? So if you're trying to sort, if you're using it for sorting, you might be able to tell different alloying agents can affect it. So current density is, though, going to affect the sensitivity and accuracy. If those become, there's advantages and disadvantages to having a high eddy current density, okay? If they're too thick at the surface, you can't see below. So you don't get what's called good depth of penetration. So ferromagnetic materials, where they form a lot of very strong eddy currents right at the surface, it's really hard to find subsurface flaws with eddy current testing. It's easier to find subsurface flaws in materials that are not as prone to building up those magnetic fields, and thus those real strong eddy currents at the surface. So that's the third point there. Current concentrates at the surface of the material, and the more ferromagnetic the material, the more of it concentrates near the surface, because you get a real strong magnetic field at the surface. Current density decreases exponentially as you go away from the coil, and this is known as depth of penetration. We'll look at some diagrams that kind of show this. And that skin effect is the last one I was talking about. That near surface can potentially hide subsurface flaws. So materials that get those real strong surface eddy currents and real strong surface magnetic fields it's harder to see deeper into them. You get less depth of penetration. It's harder to find subsurface flaws. So we have to figure out how far can we see? How deep can we effectively see into a part? And that's a term known as the depth of penetration, and then what we define as our actual distance is the standard depth of penetration. So if we look at the current density, when it drops off below 37% of what it would be at the surface, that's where we can say we can no longer see beyond this point. So below that, it's considered to be insufficient for testing. We may still pick up some subsurface flaws that have less than that, but we can't say for sure. And so what it looks like is something like this. So if we put our coil near the surface, we're going to get our eddy current strength, as highest at the surface, and it's going to decrease exponentially as we go down. So here, we say there's 100% strength at the surface, and where that drops to 37%, that is our standard depth of penetration. You can see the probe and the system forms eddy currents significantly deeper than that 37% strength, than that standard depth of penetration. And you can see too, because it's an exponential decay, that probably happens closer to the surface than what you would normally imagine, right? Most people think, 37%. If I go from here to here, 37% is probably somewhere down here, right? But we need to look at where does 37% drop off, or where does the strength drop off to 37%? That is our depth of penetration. And that is dependent on things like the type of material. It's very, very dependent on the type of material. Ferromagnetic materials, again, have this drops off, it comes over like this and then drops off much more. So they have a very shallow depth of penetration. If we look at, this is an image taken with, I believe it's a magnetometer. You have a coil, and it's actually a heat map showing the strength of, or the density of those currents, basically the strength of the magnetic field in the given area. And so in a coil, you can see it's concentrated at each edge of the coil, right? And so it kind of creates a ring. So what we get when we move our probe over a part, when we move it over a crack like this that's on a flat surface, we'll kind of get an indication one direction, and then it'll even back out, and then we'll get an indication kind of the opposite direction. So it's not uncommon to get indications that kind of look like a bow tie or an infinity symbol. You're not going to do calculations, but this is just this gives you a kind of the mathematical representation of it. So other things that can affect it are operating frequency. I mentioned earlier we can vary our frequency typically in the kilohertz and megahertz ranges. And so frequency is inversely proportional to the depth of penetration. So the higher the frequency, as we increase the frequency, what's going to happen to our depth of penetration? Is it going to increase or decrease? We increase the frequency. What will happen to our depth of penetration? Increase or decrease? When you have a fractional setup like this, anything above, anything in the numerator is going to be directly related. Anything in the denominator is going to be inversely related. So it's going to decrease. So as we increase frequency, we'll decrease our depth of penetration. Well, if we want to look as deep as possible, what do you think? What do you think the difference there is? What did I say earlier about higher frequencies? What's the advantage of a high frequency? It's more sensitive. You can find smaller flaws. So sometimes you have to balance that. I want to increase the frequency to find the smallest flaw possible, but I also want to possibly find a flaw that's deeper. So if we're looking for surface cracks that are on the front surface, what do we usually do with the frequency? Do we usually use a high or a low frequency? High frequency, we don't need to look very far in. What if we want to see corrosion that's on the back side? It tends to be bigger. We're not looking for, if you were able to open that up, you might even see the corrosion. So it's big enough you could see it if you could access the area. So what do we think, what would we use for a frequency when we're looking for corrosion on the backside of a piece of sheet metal? We would go to a low frequency. It has a greater depth of penetration. It's less sensitive, but usually corrosion's big enough we can see it, right? But you're trying to look into a lap splice where you got two pieces of aluminum riveted together, and the only way you could see it would be to drill out all those rivets and peel it back, and we don't want to have to do that every time we inspect the plane. So materials conductivity, so that we can, the operating frequency, we can vary. Our tester allows us to make those changes. How about materials conductivity and resistivity, which are inverse to each other? Conductivity, it conducts electricity better. Resistivity, it's more resistive, right? They're opposite. But so conductivity or resistivity, you can see in this equation, they use resistivity. So if a material is highly conductive, which means it has low resistivity, what will our depth of penetration be? High or low? Relatively speaking, it will be low. Remember, that's directly related because it's above, it's in the numerator. So high conductivity materials have low resistivity, they'll have a lower depth of penetration. Okay. We have conductivity tables we'll look at in a minute. And then a material's magnetic permeability. Who remembers what permeability is? Going back to magnetic particle inspection, what's permeability mean? How easy it is to magnetize something. Okay. So if we have high permeability, easily magnetized, what will our depth of penetration be? Well, I talked about ferromagnetic steels earlier. You have poor depth of penetration because you get such a thick layer of heavy magnetism, heavy eddy currents at the surface, it's hard to see through it. It's hard for the probe to see below it. So that is low. So our lower permeability materials, our aluminums, our titaniums, right? We're going to be able to get a greater depth of penetration on those. Okay. So here's kind of a comparison of that. If we've got two coils, and one is, this is showing the difference of frequency, because that's the biggest thing. Do we have, going back, didn't mean to go, yeah. Do we have any control of a material's conductivity or a material's magnetic permeability when we go to perform a test on a component? Can we change that? There's nothing we can change. The component's made out of that material. That's what we're dealing with. So our biggest thing we can change is our coil operating frequency. We have a couple other controls we can do too, but this operating frequency is the most critical of any of the controls. We can also control how much power we send into the coil. That's called our driver power. And we can also control how sensitive the tester is picking up that change in inductance in the coil. That's called gain. Anyone familiar with gain from a sound standpoint? Anyone worked with sound work? I see. Jay's nodding. I know he does stuff with that. He knows what gain is. What happens if you turn gain up too high? You get a ton of distortion. What happens if you turn driver power up too high to a speaker? You also get distortion. How many of you crack the speakers in your car? That's your driver power to it. You've never made your speakers pop in your car? I don't believe that. You're 20-somethings. Your ears are too precious. I have a blown speaker in my car because my wife had it turned up too high. And she'll be perfectly happy to tell you that. I got to change it. One of my wife loves gangster rap. You've probably never met my wife, but you wouldn't believe it when you see her. She likes it, and she likes it loud, and so hopefully she doesn't do it in her car now. But yeah, I have a speaker I got to change. So eddy current, depth of penetration, the biggest way we can adjust that, or where we can work with it, is the frequency and adjusting the frequency. And sometimes that's probably, you might have to play around with the frequency a little bit. When we go to do, or when you go to do these experiments, you will have kind of an initial setup, a recommended, like this is where you start, But that's just it. It's a starting point. You will then have to kind of tweak the settings, and the biggest one you'll probably end up tweaking is the frequency. Probably driver power and gain as well, but the frequency is the biggest one for a material. So higher frequency, we get less penetration, but it's more sensitive. So this is good for finding surface cracks. If we're trying to find things near the backside or deeper in the material, we're going to use a lower frequency. We're going to get a greater penetration. It's going to be less sensitive. We won't be able to find the smaller flaws, but typically, again, usually if we're trying to get depth of penetration, we're looking for something like corrosion, and corrosion tends to be larger in physical size than little tiny fatigue cracks. So here is, remember I said there's tables of conductivity and resistivity. And so, of different materials, and it's fixed by the material, and it's even going to change by the alloy, right? I've got aluminum on here, pure aluminum, 99.99, right? I don't have every alloy of aluminum. The aluminum we use in aviation is rarely, if not ever, pure aluminum, because pure aluminum is too soft. It embrittles too easily, right? So we alloy it to make it stronger and more rigid. So there's aluminum, we've got different bronze. And you can see there's all different things on here. Even materials that you don't think of as metal. Calcium's technically a metal, right? Tin, tungsten. There's titanium on here somewhere. Did I miss it? Or does this table not have titanium? No, I'll have to find one with titanium. But you can see here conductivity, resistivity. So high resistivity, we get greater penetration. Low resistivity, we get less penetration. Right? And conductivity, resistivity are inverse of each other. So you can see something like iron, steel, has a resistivity of 9.58 microohms per centimeter. Aluminum is only in the 2 to 2.5 range. You put an alloy into aluminum, the resistivity goes down. It conducts even better. So steel, it's got high resistivity, we'll get better penetration, but at the same time, that's ferromagnetic, and so, kind of offsets. That's kind of offset by the permeability side of it. As we saw in the equation, permeability above the line, resistivity below the line. So you got to take both of those into account. Okay. Things like copper, right, very low resistivity. It's very hard to get deep penetration in a copper part. You don't use this too often. Copper parts don't tend to crack too bad though either. It's such a soft material that they tend to bend more. They don't crack as easy. They can, but not as bad. There you go. Even air has a certain level of, can be looked at. Any material can be looked at. So this is conductivity, resistivity. Here's permeability. Remember how easy is it to magnetize? You can see, air is 1, aluminum is roughly 1, right? Effectively 1, 1, 1. Iron is 180,000. It's not even a fair comparison, right? The silver, lead, copper, air, oxygen, aluminum, titanium, even manganese are all around 1. Now that can be a big difference. It's still orders of magnitude difference between something like titanium and air. Now titanium and aluminum, you can see, are actually fairly similar, right? But there'll be some differences there. But iron is far and away different. Nickel to some extent. So the high permeability results in that much, much higher surface field, and then the induced eddy currents at the surface are much, much higher, and that blocks that magnetic field from penetrating deeper into the part. And that's why with high permeability, iron, we get a lot less penetration. It's harder to see backside corrosion in something like a piece of iron, but you can find surface cracks fairly easily. So all those things have to be taken into account. So again, when we do our parts, when you're learning to do this, you'll have kind of a starting point for where to set now again, the only control we have here is our frequency, right? The permeability is set, the conductivity set or the resistivity set by the material. You'll be able to control the frequency, and then you'll also be able to control driver power and gain. And so that's, you need to keep that in mind. You will be given kind of an initial set of parameters, and then you're going to have to experiment a little bit, adjust them a little bit, see what happens to try to get a better reading or you can affect your reading. Even things like, the reason they give you a starting value is there's manufacturing tolerance in the equipment. So you sometimes have to tweak it a little bit just because you have a different probe attached today than you did yesterday, or because you're using a different cable to connect it, or even the electronics inside the tester itself are slightly different. So that's why it's important that we record things like serial numbers of the probe we're using, serial number of the test you're using, because that can have some effect. Those manufacturing tolerances can have a small effect. So here are those different frequencies. As I mentioned, we're typically going to be, for most of what we're doing, we're going to be in the kilo and megahertz range. As I mentioned, you can go down, range from 50 hertz to 4 megahertz. Right, so I said early testers in the United States ran at 60 hertz. Anyone know where the 50 hertz comes from? Okay, which elaborate. Europe tends to use 50 hertz. A lot of the countries in the EU use 50 hertz. So that's where that comes from. So early testers, if you plugged them in Europe, you were running at 50 hertz. If you plugged them in the United States, you were running at 60 hertz. I have no idea what Korea runs at. Do you know? What's that? Korea runs at 60 hertz. Okay. They're pretty close allies with the US, so I'm not surprised. So again, for our aluminum parts, mostly what we're going to be doing, several hundred kilohertz to megahertz range. Although we'll drop it down to maybe 10 kilohertz or 1,000 kilohertz for like when we do backside corrosion type investigation. You want to keep that compromise between depth of penetration and sensitivity in mind. So what are you looking for? You need to ask yourself that when a level 3 NDT technician is setting up these setting up these tests that are going to be published into a non-destructive testing manual for an aircraft or for a component. That's one of the things they're looking at. Now, they typically know what the alloy is, so they know what the conductivity or resistivity of the alloy is. They know what the permeability of the alloy is. That helps them make that determination. Engineers are hopefully going to have some idea of where they're looking for failure points, although that's not always a perfect science. So the geometry of the part and that kind of thing. So the big key, though, is we have to make sure that our parameters are set in such a way that we can reach the expected flaw. But we don't want to send a bunch of energy out the opposite side. If we've got a piece of sheet metal, 32,000 sheet metal, 60,000 sheet metal, and we're looking for backside corrosion, in aluminum, say aluminum, we don't want to set the frequency so low that depth of penetration, if it's only 60,000, that the depth of penetration ends up being a half an inch, right? Because that means most of our energy is being basically wasted out the backside of the part. So we have to, that depth of penetration should be set, should be calculated. And again, this is a much higher level than what we're doing, but understand that will be set in order to try to focus that area, between surface and the effective depth of penetration covers the whole thickness of the metal if we're trying to do backside corrosion. If we're looking for surface cracks, we want to have some idea of how deep they might be. If we're specifically trying to find surface cracks, we don't want to be going through the whole thickness of the metal. We want to be focusing on maybe that top 10% of the metal's thickness, or the top 20% of the metal's thickness. And so that standard depth of penetration is set to match that. There's also probes and test equipment that can do multi-frequency testing. So you can have a tester that will, for a period, and again, these are fractions of a second, a period of time, will run a high frequency through the probe, and then it'll run a low frequency through the probe. And then it runs a high frequency through the probe and a low frequency through the probe. So that one's actually testing surface backside. You can have these multi-frequency systems that can increase the range of inspection, how thick of the part you can inspect. Instead of having to like set your tester up and go over it once, stay at high frequency to find surface cracks, and then set your tester and probe up a second time with low frequency, it can sit there and do both. Boom, 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 back and forth. So that's pretty slick too. So I've talked about how it works. Now we're going to look at the equipment that goes with it. So here's a collection of eddy current probes. You'll see they run from very small. The ones on the bottom left here are known as pencil probes. And we've got these two on the far left. They're pencil probe is even big. They're about a tenth of an inch diameter, maybe 0.2 inches in diameter. And then you have bigger probes. We have a probe that looks like this. We've got some probes that look like these. We've got some of these. Okay. So they're also referred to as coils. You'll hear referred to as coils, but understand that there are cases where a probe can have more than one coil in it. There might be more than one coil of wire. There may be different coils. Different coils lend themselves better to different frequencies. So you might have probes that have multiple size coils in them to be able to test at different frequencies, or those multi-frequency probes, they can bounce around. They also may be different size, have more than one coil, they have more than one coil, more than one size coil, because they can, with separate coils to drive or to create the eddy currents, and a second coil that senses them, what's known as a driver and a pickup, you can actually make two different size coils or two different wound coils that one is more properly sized for the driving function, and the other one is more properly sized and designed for the sensing function. All right, so you can have that. So you may have a probe, which again, it may be referred to as a coil that may have more than one coil in it. They come in all different kinds of shapes, sizes, and configurations, and a lot of them are, I talked earlier about things like wheel bead seats and that kind of thing. You can get these that are custom designed to fit certain profiles of areas that have to be inspected regularly. Right? Every time a wheel comes in to get a new tire put on it, they do a bead seat inspection. It makes sense to make a probe that matches the shape of the bead seat so you can just quickly run it around the bead seat without having to worry about it wobbling or sitting at a weird angle or anything else. You make it as dummy proof as possible, or you reduce the amount of specialized skill and training you have to provide somebody in order to perform that inspection, right? You standardize it. There are some, what you'll start with using though are more standard kind of general purpose probes. So the most common are flat, pencil, bobbin, and circling. This is a flat probe. This is actually a spring-loaded flat probe. And so the neat part about these, they've got this wide area. This is just a plastic base around the outside. The actual probe is this gray disc in the middle, and they're mounted on a little spring. And so when you set that on your part, you've got that wide flat disc that keeps it from wobbling, and then the spring holds the actual probe tightly against the surface so that you don't get any kind of surface breaking. You can imagine if I'm going across the surface and I have a probe that doesn't have this and I wobble it a little bit, that's going to change how much metal is directly in front of the face of my probe. And so you will get indications for that. What kind of an indication would that be? If you get indication from wobbling your probe. That would be a false indication because it's caused by process error. Okay? Non-relevant would be the geometry of the part, and relevant would be going across a crack or something like that. So these help to reduce false indications, but where do you think they're severely limited? Let's see people kind of rocking a hand. they are pretty much limited to flat surfaces. Even something like the very slight curvature of a fuselage is probably too much curvature for them to really do their job effectively. They'd be able to rock side to side, and that kind of negates the whole purpose. So these are really good for flat surfaces, like the test block you're going to test, but they don't have much use in anything besides a flat surface. Oh, there's the arrows pointing to the actual probes. I'm going to go ahead and stop there.